Hi again. So let's continue on with the last lecture. So let me try to give you a clean review of what I talked about last time. Last time was a bit experimental and then we cleaned it up. So, first thing we discussed in pure mathematical terms was what is the tensor product between two vector spaces. And you think of multiplying a vector here v with a vector here in w. This, of course, a priori doesn't make too much sense, but we realized that if you could go with the free vector space of all pairs, then at least you have a pair here in this situation, and the natural thing is to mod out by bilinear relations. Let me remind you of these bilinear relations. So, an example of a bilinear relation is, say, if you think of an element here as just a pair, so A1, B1, A2, B2, W, well, the relation should be, so this is a free vector space, so we can put a coefficient by A1, B1, W, and A2, B2, W. In mathematics, quite often we just write this symbol, and this will be the relation that we're going to mod out by this. We're going to make this equal to 0 in this quotient. You see, this will be in this vector. This is a vector space in this subspace here. This is going to be an element of this quotient. So when you of these relations, and so when you go here, is 0. So the notation, as you know, but let me just repeat, is that you have if you have, let me just repeat the situation here. If you have a bilinear mapping to some other vector space, so that makes sense here. This is not a vector space, but it makes sense to say something is linear in the first factor, linear in the second factor, so it makes sense to say something's bilinear, right? Then this thing factors through the quotient. Your map. This is the universality law that is satisfied by the tensor product and in fact defines it. But I like to construct it. So it's just all possible pairs then regarded as a vector space with coefficients modulo the relations you know about. Okay. So an element here, a pure tensor is equivalence class. Is the equivalence class of a pair here is a pure tensor. You write it like that. And if you have a basis, let's say of V, say E1 through En, and a basis of W, say F1 Fn, then the basis of the tensor product is just the pure tensors of that type. You can check it. Okay. And as a concrete example, I pointed out to you that the endomorphism, for example, can be regarded, using this universality principle, as V tensor V dual. These are the linear operators on V itself. And so if we have one basis here, we just take a basis, frame, depending on how you want to call it, En, and on the dual, take the dual basis, En. So this should be the dual basis. And the basis you get for here is just, so an element here, in the homomorphism regarded as a tensor, can be written as a linear combination of these basis elements. And that is the matrix of an operator. That is the matrix of an operator. An operator is canonically, if you have bases, a sum of rank 1 operators. Right, these are rank 1 operators. So that's that guy, that tensor product. And now, I would like to go to the full tensor product of one vector space. So I want to define the full tensor product of a vector space. And in fact, this will be, it depends how you think, but this will be always, by the way, the constants are always in this. This will be the direct sum of the k-fold tensor product of the vector space with itself. Let me just make sure the notation is clear. The k-fold tensor product of itself means k times recursively. But I prefer to think of this in a good way, at least for me, as you take the free algebra, the free associative algebra on V. So you start with a vector space and you want to multiply things together as much as you can. So not just a vector space. Multiply, that's the free associative, no relations whatsoever. Just a multiplication, but nevertheless, modulo, in this case an ideal, the relation ideal. So the relation ideal, this is the two-sided ideal. Professor Schub mentioned, underlined that last time. This is the two-sided ideal generated by the obvious relations that you want, that you would use if you just write down symbols. As I say, physicists do, and they know what they're doing. They're just writing down the symbols. They don't even think about this stuff, but we really want to, and they don't need to because they understand, but we want to look at it as a formal object. So generated by bilinear relations. And for example, let me write one. Say a k-fold, something in the tensor product k, so something like W1 to WK minus 1, and then in the middle we have some relation A1, B1 plus A2, B2, WK plus 1 someplace, I don't know, down to W, big and some huge thing in a product. So this would be in the n-fold product of V with itself. This should be equal. So equal means minus in the relation ideal. Minus this thing should be 0. So minus, well, let's put a coefficient out here. A1, W up to WK, and then in V1 in the middle here. And then go on with this stuff. Well, I'm getting tired already, so A2. B2, typical multilinear relations. Oh, I'm sorry, I should write here, I wrote bilinear, so this, I should write here multilinear. Relations. Okay. So, typically then, an element of the tensor algebra, the full tensor algebra. It's an algebra, it's an associative algebra. An element of this full tensor algebra is a finite linear combination, AI, VI. What does that mean? You have to get used to multi-index notations, right? So AI, VI, would be AI1, IN. That's a well, I'm writing some here. sum over some I, some finite set, AY1 through, say, a K tensor. Well, yeah, say a K-fold tensor to make it nice. So AI1 through AIK, VI1 tensor VIK. And these are just the projections in the equivalence class of the element of the problem. Okay, I'll put some here to make everybody happy. Okay, so this is okay. Now I would like to go back. My original motivation was some of the basic stuff in quantum mechanics, so I would like to go back and re-emphasize what that was about. Okay, so everything, we can be happy now. We have all this, we know what we're dealing with. So let's go back to the Weil algebra. So the motivation was the first, well, not motivation, the first thing we take is this direct sum, which I tried to motivate in the cotangent bundle of a vector space. And this thing has almost, well, a canonical inner product, canonical alternating bilinear form. I'm going to today use over C. It doesn't matter in any of the discussion right now. The form is defined by, as I defined it yesterday, well, second applied to the first minus the first applied to the second. When one defines a Lie algebra here to be, and this was confusing to some people, I'm now using the scalar C. So just a symbol 1, which physicists will call vacuum, but this means just a copy of C with a distinguished basis. You have one-dimensional vector space with this basis. This is a Lie algebra. By the bracket of first, if you have two elements in the W part of it, I have to say what's going to happen to them. Then I define the bracket of these things. Well, to land in this multiple of the vacuum, namely just this alternating form times 1. And the agreement is that the vacuum can be used with everything. So all stuff. That defines the Lie algebra structure. Remember, Lie algebra is equipped with a bracket, antisymmetric. The antisymmetry is guaranteed here. You see, this is antisymmetric, and therefore the bracket is antisymmetric. And this antisymmetric bracket is bilinear, should satisfy the Jacobi identity, and in fact does automatically here. So that's a general construction, and this algebra is then called the Heisenberg algebra. But in fact, if you take bases, so what we're going to do something amazing here. So there's an amazing jump. That nobody was satisfied with yesterday, and I'm happy you weren't. But the amazing jump is you take a basis of V and a basis of V star, not the and a basis of V star. No, this is a dual basis. And then And of course, any mathematician sits around and says, well, okay, I have no problem, there's no problem. AI and AJ dagger and 1 and all this stuff, that's certainly in this Heisenberg algebra. Right, I mean, there they are. There's B and B star and whatever, it's there, no problem. Right. But when you get excited is when some physics friend of yours tells you, well, I might be interested in this thing. Something like that. Right? Just put your bunch of symbols down. Well, the way of thinking about this, which is correct, is you look at all possible symbols of this type, which obey the obvious relations that are built into this situation. You look at all these symbols which obey the obvious relations which are built into this system. Okay, the map one, which are caused by this relation. So the way to make that precise is to define the Weil algebra. Let's make it script because it's very big. Weil algebra equals the full tensor algebra of W. Here the unit is automatic, so I don't have to write 1. Okay? Modulo the relation. Well, the relation is x tensor y minus y tensor x. This should be equal to a of xy times 1. Okay. So x and y are in W, and this is meant for homogeneous elements in W, and this is a relation. This should be the case, because that's what we've defined it to be here. Okay, that's what we've defined it to be here. Okay. So the objects are in the Weil algebra. This makes perfectly good sense. Okay? It's just that you know when you're in the Weil algebra, we're in this quotient. That means these things are equivalence classes, which we no longer write as tensors. Okay? So in the Weil algebra, we don't write something like AI tensor AJ dagger or something like this. We don't write that. That doesn't make any sense because that's really the tensor algebra. We're downstairs in this quotient where we're thinking modulo these relations. We don't write that. What we write is we write simply AI AJ dagger. Okay? And we know that there is this relation. Any problems? No problem. Nobody. Once we have all of this tensor language, we know what we're doing. So that's what the Weil algebra is. This Weil algebra is very interesting. There's several things. Let me just write down what the relations are. So the relations are called the canonical commutativity relations. And without knowing what a boson is, this is sometimes very mysterious things for us in mathematics. These are, in some sense, quasi-particles or quantum states or something, or operators. These things, you should use the word, if you hear a physicist talking about boson, he may be probably thinking about this. These things. So what are the canonical commutativity relations? Let's see what they are. Well, let's see what is A, I, A, J minus A, J, A, I. Okay, just for fun. So that we know what that is in this quotient, AI, AJ minus AJ, AI, it's up there. That's in the ideal, so that means it's 0. No, not 0, it's equal to whatever, minus something 1. So that's equal to A of AI, AJ times 1. And don't forget, these things are in B. right? If there's a dagger, they're these are annihilation operators, which are in V, and if you have something in V, there are no phi's in that definition. It's just V, phi's not there, phi primes, I mean, nothing's there, so the answer is 0. Okay? The answer is 0. So you see that these things commute.
Professor, is it here AIAJ the basis of B, or is just the elements in the W?
Say it again, what?
Here AIAJ, they're the basis of B, or
That's right, that's right. By the way, in any discussion you will have with physics, they have probably already chosen some basis, and that's what I've done. If I hadn't chosen a basis, I couldn't do this, right?
I mean, according to your definition, A of AIAJ should be 0, I think.
Yes. 0.
No.
Yes.
According to my definition, AI, AJ minus AJ, AI is equal to A of X of AI, AJ. Right? And what you're thinking is 0 is right. A, big A, of AI, AJ is 0. Right? That's what you're thinking. Okay? They commute in the Heisenberg algebra. Okay? And I don't have to tell you that the same thing with the dagger, with the creation operator. Okay, that's the reason this word canonical commutativity relations is used here. You see, these commute among themselves, these commute among themselves. If you write down some huge option here, you might want to simplify it and use these canonical commutative relations. Now what is interesting maybe is AI dagger AJ. Okay, well let's look at it. AI dagger AJ dagger minus AJ dagger AI. What I just said was stupid, right? AJ AI dagger, right? We're testing whether it's going to commute or not. Right? Is equal, well, I think if I've gotten this right, this is delta ij times 1. Right? So they commute unless I is equal to j.
Minus 1.
Huh?
Minus 1.
Minus 1, have I got the sign right? Okay.
No, wrong.
Yeah, it's a sign, it's very good that Professor Schub is here because I will always get a sign right. And every physicist knows what are the good signs. It's very important to really just say, okay, you're right, I got it. It's okay. So that's what that is. So here's a relationship. They commute unless I is equal to j, but if I is not equal to j, then let's look what happens. A1 dagger A1 is equal, just for fun, to A1 dagger plus 1. Right? Plus 1.
Minus 1.
Minus 1. Minus. Okay? Minus. I can't get it right. Okay, that means if you have a monomial, which is very complicated, and you're trying to simplify it by putting things together and so on, right? Trying to really understand with creation, annihilation, and so on. If you simplify by changing these things around, you pay a price. Okay? But the price you pay, you see, is with 1, so that you have to put that 1 in there, and what happens is you go down your monomial, you get a new monomial by exchanging, but you pay the price of a term that's of 2 lower orders. Right? Do you see what I'm saying? You have a monomial of order 25, and in the middle you want to exchange something like this. Okay, you exchange. Life is capitalistic. You have to pay a price. What you exchange, and the price is minus 1. Well, minus 1 goes in there, but I mean that's just minus 1 is 1. So it goes in there, and you get minus a monomial of 2 lower terms. Terms 2 lower, right? Okay. Well, that's one reason for the fact that the Lie bracket here, and if you have any associative algebra, you have a associated Lie bracket that you go down. I mean, this really is one of the reasons that it works out that if you take something of order k or less and something of order L or less, and you write the bracket, so let's say alpha beta is by definition just alpha beta minus beta alpha. It's an associative algebra, you have this bracket. This thing, if alpha is here and beta is here, then alpha beta is in this lower order. A very interesting fundamental fact, and I noticed yesterday that if k equals L equals 2, or U numbers, then this says that omega W2, namely the terms of second order, so that all the monomials you can generate of second order or lower form a Lie algebra. And that is really, really interesting fact. It's actually easy to see which Lie algebra it is and so on. Well, that was the Weil algebra, a little bit introduction to the Weil algebra. The headline word here is just for us as a word, we don't understand much more, is these are operators of, these are not operators, this is just formal, but if you think of them as operators, they're of a bosonic type. So let me just say there's another word in physics. And this has to do with another algebra that I will now introduce. So there are two fundamental algebras in this elementary quantum mechanics. One is called the Weil algebra, and the other algebra is called the Clifford algebra. And I'd like to introduce the so-called Clifford algebra. By the way, it's completely obvious this Weil algebra is infinite dimensional. You can just write down, I mean, monomials, in some sense write down monomials as spanning, and you can see that it's clearly infinite dimensional. Okay? So the Clifford algebra, fortunately, the fermionic situation, which makes life very, very, very much better for so-called fermions, is implicitly finite dimensional. Okay, so the beginning point is this. W, again, is V plus V star.
Professor, can I please ask, what if, so when we do quantum mechanics, what is V? I mean, is R3 when you start with?
V is a n-dimensional vector space.
No, I mean if you want to like model the real space.
I'll talk about it in a minute, okay? You should think now it is an n-dimensional vector space if you want to use this notation equipped with the basis. Okay, because I really didn't have this discussion of AI and A dagger and so on. Okay. But please do not, it's a very fundamental, at this step of the discussion, please do not interpret any more than I've said. It's just this. Okay? But I definitely want to get to your question in 2 minutes or 5. Okay? I just want to comment on this Clifford algebra or fermionic side. This thing is equipped with a symmetric product. And of course its obvious definition. S of V plus V, V prime, V prime. It's the second applied to the first plus the first applied to the second. Symmetric product. It is interesting that we start, and I got confused when I began trying to understand what's going on in this business, is we started here with an alternating form and ended up with canonical commutativity relations. Yep. You would think with alternating somehow psychologically it should be alternating relations. But the reason is alternating means that if you put it on the other side, you see if you put it on the other side, it's commutative. That's what's here. We have symmetric form. We're going to end up with alternating relations. Okay, the symmetric form is that. Well, okay, I don't care. Let us go to the full tensor algebra. Let's call the Clifford algebra the full tensor algebra, of course, including 1. So let's emphasize that this is, again, this is a graded algebra. So the terms of degree 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on make sense at the level of tensor algebra. So this is going to be modulo sum relations, and this, of course, these relations kill the gradation. Just as here, the filtration, in terms of degree k or less, degrees L or less, that all makes sense, and it will be the same thing here. The relations are more or less the same type. So what is this? This is the fourth thing, modulo x, y. Now, this is symmetric. So the correct universal algebra discussion of this matter is the ideal generated by x tensor y plus y tensor x minus s x y 1. Okay? So we want to go to a place where we can multiply vectors. You see, this is incredibly complicated here, symmetric form of this stuff. The idea of universal algebras is we want to forget this stuff and just somehow the correct bilinear form is just xy plus yx. Here the correct bilinear form is the Lie algebra bearing xy minus yx. Here it is xy plus yx. Okay. Well, okay. So this is the ideal, two-sided ideal generated by this. This is called the Clifford algebra. Okay. So let's see what happens with our basis stuff here. So what it says is that AJ plus AJ AI, right? X tensor y tensor x is equal to s of x, y times 1. Well, as of these two things, we look upstairs, there's no phi around, it's the same discussion, there's no phi around, so this is 0. Right? There's no phi up, you see, these are vectors in V. You know, this basis vectors in V. So that means that these things anti-commute. Okay? And of course, the analogous discussion for the things with the dagger. That means the dagger things anti-commute. Oh, did I do something wrong here? I did something. I'm sorry. Of course I meant exchange. And for this reason, we call these relations here, plus the third one that I'm going to discuss, the canonical anti-commutation relations. Okay? So, C-A-R-I, I thought this was something you drive, but it's not. These are canonical commutivity. Anti-commutative, thank you very much. Anti-commutative. Anti-commutativity, I don't know really. Now I haven't done the third one, I have to do it, don't I? So it's I, so let's try to do it parallel. AI dagger, AJ, plus now, AJ, AI dagger. Well, is equal, I guess it should be the same thing, I hope. The sign convention has to be the same, I hope. It should be equal to delta I squared with minus.
No, plus.
Now is it plus?
Well, you can't make a mistake on this one.
Huh?
Everything is plus here.
Everything is plus. Okay, okay, fine, thank you. Okay, so you see it's anti-commutative up to a vacuum. So again, you can reverse these things. They're anti-commutative when you reverse, but you pay a price in the vacuum. So you pay a price at lower order, right? This is what I talked about before. These are the relations. This is a Clifford algebra. This, as you see, is clearly finite dimensional. Yeah? You see why? If you have a long enough term, you are bound to have two things of the same type. AI and AI, some AI and some other AO will appear there. Now I have fun, yes, and use the alternating property out, okay? This is only finite dimension. So this is finite dimension. Okay. These are the two basic algebras at the beginning of quantum mechanics.
Professor, can you explain again why it's finite dimensional?
Okay. So you know that if, okay. Okay, so what is AI? AI. Let's have fun. AI times AI. Okay. Use the anti-commutativity relation. It's minus AI. AI. Yeah. So it's another way of saying that AI is 0. Okay. So what I just said is you have some big monomial where you find A1 in it twice. Then you can do all sorts of things and put the A1 next to the other A1 by using some, yeah, you see, and you can see, you make, okay, you can argue, you can see what you do, but the fundamental point is just this. So. Okay, now I would like to get to a question which I think Mihai implicitly was asking. I will attempt to answer. So, these are abstract algebras. So this is abstraction. And when you have some abstract things, this is now really something you should think about in private and discuss with your friends. You have some abstract objects, extremely abstract objects. Then you want to evaluate these things. This has nothing to do with course evaluations of my course, or evaluations of a list of beautiful guys. I mean, this guy's really great. He gets a 1. You give me a 3 on the old. Okay, so, well, 3's just average, you know. So, look, quite often it is such that you have a letter named F. Right? Really, I'm serious about this. Yes? And you evaluate this thing at a point. Right? Right? It's quite often you have a space of things called functions, but you don't know what you're talking about until you evaluate it. This is a space, an abstract algebra, and you don't really, this is what you're talking about in some sense. I'm trying to make sense out of your question. I think I did. You run to know how you're really going to evaluate this algebra. Okay? So let's talk about this notion of abstraction to evaluation. Let's talk about here the abstract object, let us say, is the Weyl algebra. some abstract object. Well, this thing, through an evaluation, which is called a representation, it's a good word, right? Because you're representing the algebra by it's doing something. In quantum mechanics and sometimes in classical mechanics, you evaluate some abstract thing as a function, and suddenly in quantum mechanics you evaluate the same abstract thing as a differential operator. Say it again. In physics letters, P and Q, sometimes P squared plus Q squared is the norm function on some space. I mean, it's just the norms, but P and Q are coordinates. I'll talk about this in great detail in my next lecture. P and Q are coordinates on some space, and P squared plus Q squared, it's just like X squared plus Y squared. Okay? You just happen to evaluate the letters P and Q from some algebra as functions, but you could evaluate P as the partial derivative with respect to P, and P squared as the second partial derivative with respect to P, and Q you evaluate as the partial derivative with respect to Q, and Q squared is the second partial derivative with respect to Q. So the evaluation of PQ as a differential operator is Laplacian. You understand what I'm saying? Abstract object can be evaluated in different ways. It is quite often the case in classical mechanics you evaluate the abstract object as really a function. These functions are called observables. In quantum mechanics you're usually evaluating these things as operators. It is very interesting. Suddenly you evaluate something as an operator and you're interested in its spectrum. Interesting things that make physical sense. These operators should be Hermitian or something so that you have eigenvalues, and so you should be interested in these eigenvalues. They might be called energy levels and things like this. Suddenly you have some very interesting thing evaluating, you see, some abstract thing on the one hand as a function, on the other hand as an operator. Very interesting, right? What's interesting is somehow to be able to compare the classical mechanics and the quantum mechanics. The spectral things of this Laplacian compared to the Hamiltonian system that is generated by this P squared plus Q squared, and the dynamics of the Hamiltonians. I will explain that exactly. But I just want to say now that you have abstract things, and by the way, get it in your head that physicists are actually more abstract than mathematicians. You think they're doing physics and here's temperature and all this stuff and all of that. They are more abstract if you think of it. You have to see that this is just the biology. This is just the stuff. Don't worry about it, man. Okay? Well, we don't. So I want a representation of this Weyl algebra. And what am I going to do here? I'm going to represent it as an algebra morphism into another algebra that I like. But now Mihai likes this because it's an endomorphism algebra of some vector space. Okay, so linear transformations. Okay? And the endomorphism space that I'm going to talk about is the symmetric product of the dual space. Now, don't worry about it. We're starting to understand that we can be abstract. Everything's cool. What is the second symmetric product of the dual space? Now, come on. Let's have some fun with the dual space. So if I take F and G in the dual space, I know how to evaluate these things. Actually, they're functions, right? Well, yeah. And, well, my granddaughter doesn't quite know how to do this yet. But she would say, well, let's look at this polynomial. Okay? Right? Right? She would say, look at this polynomial. The product of two linear functions is a homogeneous polynomial of degree 2, right? Right? x1 is the first function, x2 is the second function. The product is x1 times x2. Hey, I'm doing exactly what I've been doing for 2 days. take f and take g and write down f times g. Okay? Everybody's a mathematician here, there's some physicists here who know everything much more than we know about it, that's good. The f times g, you say, hey Jack, I don't know what f times g is. And they say, well, okay, think of it as a tensor, f tensor g. Okay? Then you say, that's not a polynomial. Why is it not a polynomial? Because, for example, x1 times x2 is the same thing as x2 times x1, or? That means you must symmetrize your considerations. It's not just some tensor. It is a symmetric tensor. Right? So what this is really a symmetric tensor in the symmetric algebra of two tensors. And the symmetric algebra, let us say, of K tensor is the full tensor algebra. Now we're having fun every day of the week. Modulo the relation. Right, this is, you get used to this and you can go home and do it before breakfast. So then what is the relation? Well, I think it's pretty clear what the relation is. Isn't that the relation? Of course, when I write the relation, equals 0 is what it means. Okay? So-
is it just the S2 relation or SK? Because here you have case.
So
Well, here I'm just talking about homogeneous polynomials of degree 2.
Yeah.
so you take the quotient over
Oh, I'm terribly sorry. Of course, you're right. Okay. Well, I mod out by this relation. I'm modding out by that relation.
So you mod out by the kernel of the alternating operator?
Huh?
You by the kernel of the alternator? I mean, is that the kernel of the alternator?
I'm modding out by the relation xy minus yx. That means in the quotient xy equals yx.
But if you say that that thing is 0, doesn't that mean that the alternator of xy is
I don't know what the alternator is. What's the alternator? Sounds like something in an automobile. By the way, Sebastian Vettel had problems with, I think, this, something like this. What do you mean by
the
alternator?
alternating function a?
I'm modding out, well, maybe. It's maybe related. xy minus yx is 0 in the question. That's all I care about, okay? And then I've gone to the symmetric tensors. And the symmetric tensors are therefore, you can interpret them as polynomials, you agree? Okay. So this thing here can be interpreted as a homogeneous polynomials of degree k on V. Okay. Well, you can do the full thing. We'll get this out of the way, so let's do the full thing. SV, this is the full tensor algebra modulo this relation. Okay. Homogeneous polynomials. This is the polynomial ring on the vector space V. Okay. Oh, I'm sorry. I'm of course interested in this, but it doesn't matter. Okay. Okay? Where am I? I'm trying to answer Mihai's question, where in the devil does this thing really do something? This Weyl algebra. Okay? So I'm looking for a representation of the Weyl algebra on something, and it will be represented on the polynomial ring of the vector space. That's an algebraic geometric expression of what this tensor thing is, the symmetric thing is. The symmetric thing, if you write it out, is the direct sum over K of the K-fold symmetric products, and these, of course, the homogeneous polynomials. It's just a statement that every polynomial is a linear combination of monomials, right? Of a certain degree. I don't, yeah, okay. Okay, fine.
They are symmetric polynomials.
No!
No, they're not.
No. Maybe I've defined them in some wrong way. They should not be symmetric. What I want is that z x1 times x2 equals x2 times x1. A symmetric polynomial,
Okay, so you don't want them to be.
a symmetric polynomial, this is very important to say, a symmetric polynomial, okay, it's clear. It's very, I mean, these things are tricky. I'm very happy you make all these remarks. Yeah. A symmetric polynomial, let me write down an example of a symmetric polynomial. P of x1 through xn is what I call a Newton polynomial. Well, you know what a Newton, I talked to you about them already. x1 to the k plus xn to the k. I would use the word symmetric for this kind of thing, letting the permutation group act on the variables in that way. But here, this relationship, wherever it is, here, is just that you can read x1, x2 is the same thing as x2, x1. Okay?
Oh, yeah, so we don't differentiate between polynomials that are actually the same. That's what we see, no?
These polynomials are the same. Yeah, it's defining sameness the way we understand it. Right.
So Professor, here actually you mean that, for example, you have a monomial of several terms that if you permute these terms, they will be the same monomial by this relation.
Yes.
Okay.
Yes.
Because I'm a bit confused at first because you only write like x and y, not for example x.
Yeah, but that's any two pure elements. So you just apply that. You apply this relation any number of times you want, and then you prove the theorem. Well, it's not a big theorem, but you prove your theorem. I'm sure you can prove deeper theorems than that. Okay, but then that's the theorem, right? Okay. Okay. So that's what's going on here. This is symmetric algebra. These are polynomials. Okay, so I think everybody will be very excited if I can tell you the fundamental representation of the Weil algebra is really on this thing here. This is the way it acts on this space. This is the fundamental representation space of the Weil algebra. I'm going to tell you what it is. Maybe I will clean something here. Again, you see it's a very big infinite dimensional space. It's, by the way, very important that it's infinite dimensional. We will find, in fact, later on complex conjugation on this space, so that's nice. We will find a Hilbert space structure on it. On the completion of it, it's now an algebraic space, but later on we will find a Hilbert space structure. This is somehow the fundamental representation at the beginning of bosonic physics. So, I have to tell you what happened. Okay, let's really just be very naive now. So we have W in VW, and W of course is contained in the Weil algebra, you know. And I have to tell you, I answer the question, how does W act? See, representation is taking something over to your favorite place and let it do something. I think in terms of symmetries, rotations, or various things. Or maybe it's a differential operator. Or how is it acting? Right? So how does W act? I have to tell you this question, answer this question. How does W act on where? On the symmetric algebra, on polynomials. Okay? have to tell you how it acts on polynomials. Well, let's see here. So W was equal to V, well, the vacuum has to act as the identity, so I don't even talk about it. So that's that. So let me first take something, so let's take W equal to V in V and see how it acts. Okay? How should a vector in V act on a polynomial? Let's write that question in clear text. How does a vector act on a polynomial? So how does a vector V act on a polynomial? I don't care, P. This is good. Now, if you were studying multivariate calculus, you know, calculus in 2 variables or 10 variables or something, and you look at a polynomial, and let me be motivating about this. So you have some vector V in space, and this line in space is V, and you have some polynomial function on V into the complex numbers. You have this vector V, and you want to know how should it act on a polynomial function. By the way, in the beginning, all physics functions are really in algebra, algebraic geometric functions. Later on, we make completions to have power series for the analysis and so on. How is a vector V acting on a polynomial? I used to give people money for answering good questions. But I don't have any small enough money for it. But this, I have 2 R's, but I need it. How does a vector V act on a function?
You just apply the functions on that vector, because the function is just a monomial.
Okay, you can apply the function on that vector, yeah. And you get a number. Right? But I have to ask a polynomial, it has to act on a polynomial ring. So I want to get the answer to be a polynomial, not always a number. That you would kill the whole phenomena if you just evaluate. No, that's one of that. It's great. It's not stupid. We were talking this at night. This is not at all stupid. You evaluate the, yeah, what else? Any other ideas? A vector should somehow act, I'll give you a hint, vector should somehow act on a polynomial. There's only one way, partial derivative in that direction, or? So, let's call delta V of B equals the directional derivative as I defined it of P. Isn't it true? I take the line, I look at V, it's completely clear. I differentiate the polynomial, right? It's good, it's the first order differential operator. I told you, you represent these things as differential operators. Okay? Okay. I'm getting very, very excited. So, I have polynomial on the right, so V goes to differential operator V. That's great. Okay? Now what else do we have in this Weyl algebra? At least at the beginning of the Weyl algebra, we have V and V star. So let's talk about here on this blackboard here, let's talk about a phi in V star. Okay, let's ask the stupid question. How does phi, that's a linear function, act on polynomials? So, you give me a polynomial, and you have to hit it with an operator, phi. How would you hit it? Phi is a linear function. What would you do? Is there anything wrong with multiplying the polynomial by that linear function?
Just multiply.
Just multiply, right? I mean, you have to, okay, that's multiplying in the symmetric algebra, of course. You get if you hit a polynomial with a vector by differentiating, and that polynomial has degree 27, What is the answer? 26. If you hit a polynomial by a linear function, what happens to the polynomial? It goes up. If you believe that these operators are called creation and annihilation operators, and you believe that the degree of a monomial is some measurement of the number of particles in the system or something, with partial differentiation, you annihilate particles. With multiplication, you create articles. These things are represented as annihilation and these operators. Multiplication, so phi goes to the multiplication operator, where it means multiplication operator of phi is just in the symmetric sense, you multiply. Okay? Now, you weren't too fast on that because you're nervous, but you have to admit that's about the only thing you could think of, right? Just differentiating and multiplication. So, W, which is equal to V plus phi, so W goes to differential operator plus multiplication operator. Okay. Well, these operators are defined at the level of W. So this gives us a mapping from W into the symmetric algebra here. However, this definition, because these operators preserve the relations, the way things work out, you have to check, because they're going to a quotient now. Right? The violent algebra is not just W, it's the whole tensor algebra modulo the relations. These operators preserve the relations. They then give you a representation of the full Weyl algebra, and that is called the fundamental representation of the Weyl algebra, and this is what the Weyl algebra is doing. It's acting on polynomials by, at least at the first order, by differentiation plus multiplication. Now, I challenge you to think a little bit more about that, because in the Weyl algebra, this is an algebra. That means you have huge, complicated, multiplicative combinations of this stuff. You might get excited about a term like this. What that could mean. What that can mean is I've represented an element of V as ddz, and I've represented, in one variable, I represent an element of V star as just multiplication by Z, and now in the Weyl algebra I have the product, right? Well, that makes sense now. The 10th, I add the two, that's just the elementary thing, and now to the 10th power applied there. This is a huge, complicated representation of the Weyl algebra, which is really, really fundamental. Okay? Any questions? I see everybody's happy. Okay? So I have a little bit of time today. Let me then talk. Yes?
Could we also use ordered polynomials? Could we also use ordered instead of symmetrized polynomials?
What kind of polynomial?
Ordered.
What does that mean?
Everything put in a normal order.
Sure, because you can always, so that, you understand what he's saying. He would say, I would like, instead of just random order or something, I would like to have some unique order. And so, as you were talking about the monomials, Z1 to the I1, Z2 to the I2, and so on, and the answer to Professor Zhu's question is, of course, you can take this representation of it. Sure. Thank you. Okay, let me say some more. Let's go to the Clifford algebra. So now we're going to Fermions. go to Clifford algebra.
Well,
Let's recall what's going on. This was, remember what this was. This was a full tensor algebra modulo the relations. And these relations is the ideal generated by x, y, plus yx, plus y, this thing, yx, minus s of xy times 1 for homogeneous elements in W. Okay? Well, I'm going to start with a Clifford algebra. This thing, let me call this C. So C is a Clifford algebra. It contains W. What I'm going to do is at least define this on the lowest level possible, and then show that it extends, just as I just mentioned, to the full tensor product modulo relation. So I have to take an example here, V. And I want to know what V is doing somewhere. Right? I want to know what V is doing somewhere. Okay? And in order for the relations to work, in order for the things to really go through as they did here, as I indicated they did here, you must put here what is called the exterior, in English, exterior algebra. Okay? The Grassmann algebra. I don't know what is it. In German, it's äußere algebra. But what is it exterior algebra? I can't remember. Okay, so I have to tell you what this is.
V star?
Hmm?
V star?
Oh, V star, thanks. I have to tell you what this thing is, okay? Ready? Go. Well, the exterior algebra is, well, it's the full tensor algebra. You're getting tired of my full tensor algebra, but modulo relations. Well, the relations are not the relations that we had before. This is the alternating relation. So the relation is the ideal. It's x times y plus y times x. For all homogeneous elements of degree 1 in W. Okay. And, okay, that means I forced the relation here to be alternating. Okay? So this is this element, and now you see what I will, if I write down, let me take two elements here. By the way, in supersymmetries, very often we call them C's here. So I take two elements, and C1 and C2, and everybody in the game says C1 is equal to minus C2. I mean, C12 is equal to C21. Okay. It is so. If you read, by the way, if you mix these two things of bosons and fermions, you will get what is called a supersymmetric situation. And you will have particle operators that are commuting, some of them, and some of them are anti-commuting. Okay? And the commuting ones are from the Weyl algebra, the anti-commuting ones are from the Clifford algebra. Okay? Get used to it, some variables commute, some variables anti-commute. Get used to it. If you're a student at Lomonosov University in Moscow, where physics and mathematics are taught really systematically together, with great mathematicians who really also know physics, they do this all the time. Okay? Don't worry about it. Some variables commute, some variables anti-commute. That's it, basta. Now I give in a little bit to you guys who are worried about symbols, so I will call the product here, so giving in, here, we call the product the tensor wedge W. Okay? That is the product that results in this Grassmann algebra. We call it Grassmann algebra, exterior algebra, which means a full tensor algebra modulo these anti-commuting relations. We call this V wedge W, the wedge product of V with W. Okay? That's this thing. So this means that C1 reg C2 is equal to C2 with minus sign, C2 reg C1. But I don't give in to making a new symbol in the symmetric algebra. I just write AB. And it's explicitly, just as in Riemannian geometry, I was asking, what in the devil does this symbol mean? He asked me, what does this symbol mean? Or what does this symbol mean? The symbol means the symmetric product in the symmetric algebra at dx dy means simply that this thing is equal to this. This means dx times dx. Here, dx times dx is 0, right? Because it's alternating. Right here, dx times dx is something you find in Riemannian geometry. Okay. So we use this product thing. All right. Very good. What's going to happen? I take something in here, which is, let's think, I think of this as a multilinear form on V. An object here will be a multilinear alternating form, just like a polynomial, but it's a multilinear alternating form on V. Let's call it omega. Okay? Multilinear alternating form. You know what I mean. If you permute the vectors inside this form with a permutation, what comes out in front is the sign of the permutation. Okay? That's such an element. Now what can I do? So question, how does V act on omega? I give you an alternating form, maybe a bilinear form, I don't know. Alternating form, what can you do to it with V to make it act? Well, wait a minute, let's take our intuition further. The stuff in V should be annihilating. That's the way things are set up here. So somehow the degree of the form should go down. You see some way to take an alternating form in 20 variables and get an alternating form in 19 variables.
Put the V inside it.
Yeah, why not? Just put it inside.
Yes. And
Okay.
get-
Well, I think Clay was right. Just put it inside. The convention is, the notation is called contraction of the form with the vector. Contraction means it's the intuition that you contract, you go down. So here, then it is V, so it's called contraction. It's always with iota. V applied to the form omega is omega, and you put V in this is what Clavis has in the first, I indicate the rest of the arguments are here. You put V in the first argument. You evaluate it. This is clearly an annihilation operator because it pushes down the degree of the form. Okay? So iota is defined. Well, what does phi do to a form omega? Well, phi is a linear function. Okay, that's a one form. Linear function is a one form. That's nothing about alternating or something. Multiplication, but what is multiplication? It's this alternating multiplication, right? Because we have to stay alternating. So it's the wedge product. So phi, it's called epsilon in my language. Epsilon for exterior multiplication of phi of the form is just phi exterior multiplication. Guess what? This extends to the full Clifford algebra. First of all, it's only defined at W, but these relations are, in other words, the relation of, let me try to be very careful, W, which equals V plus phi, acts by contraction plus multiplication, wedge product, exterior multiplication by phi is the action on the exterior algebra of V star, which is finite dimensional because it's alternating. This is called the fundamental representation of the Clifford algebra. So you have two things, fermions, bosons, Clifford, everything's finite dimensional in Clifford algebra. This thing is finite dimensional. This is an algebra representation. Don't forget, this is highly non-trivial, contraction of forms, multiplication, and so on. I find this more non-trivial because of the explicit involvement of differential operators. Yeah? Yeah? It's very interesting. This is big stuff. It's huge stuff. You see it. Yeah? And this is the basis. I will stop here, but this is the basis of a lot of interesting developments. So I wanted to give it to you. If you ever get interested in following through, I don't know if in Professor Schupp's quantum mechanics course, it might be interesting to see what all this stuff really means, because this is just formal algebra in some sense. Okay.